Good afternoon, everybody. Welcome to a wonderful Wednesday afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Now, I do have to talk about something personal, and that is you guys have been really nice to me, and I appreciate that. And because of that, take Monday off. Don't come to class Monday, just take it off. And if you're having any other classes at ECC, take them off too. And if anybody asks, tell them Dr. White said so. So take Monday off. It's Labor Day, so we all have Monday off. And I won't have a lecture on Monday, and I won't have my office hours. Well, maybe. If you need help, email me and I'll show up to my office hours. If nobody doesn't, well, then I won't, and I'll take Labor Day off. But that's my special Labor Day gift to you. All right, what I'd like to do today is, as I mentioned the first day, Monday, we're going to lose 3 hours of lecture. And last Wednesday and this Wednesday, normally we'd have 50 minutes of lecture, a break, and then do the lab, and then you can run away or walk away. You don't have to run away. But in order to make up that missing time, what I'm doing is normally today we'd have a longer lecture, and then we'd have check-in the lab. Well, we're not going to ECC for the lab, so you don't have to check in. So I'm going to go through stuff. The first thing I want to go through, as the three of you mentioned, that I probably didn't, now I got to open it because I didn't even open it, is the alkanes, cycloalkanes problem set. So give me a All right, let's go through it. Now, one thing I'll be doing all semester when we go through a problem set, I'll do one page at a time, and I'll do a couple, and or even before I do a couple, if you'd like me to do one or two, whatever, ask. Remember, in my class, there's no such thing as a dumb question. Ask, you're here to learn. All right, let's go through it. All right, everybody. Can you see alkanes problem set? Thumbs up, people. Thank you. All right, first question, which is an important skill you should have. How many carbons are in the longest chain? And if you notice, I was very nice because I didn't put any hydrogens in there to confuse you. Now, A and B are pretty straightforward. Let's look at C and D. C, what's the longest chain? Well, across is 5, but there are 2 other chains, 1, 2, 3, 4, 1, 2, 3, 4. So 5 is the longest chain. And if you notice in D, there are 2 ways you can get to 6. There's another chain, 1, 2, 3, 4, 5. But as I said the first day, we're using some high-level math skills I expect from you, and you should know what numbers are larger and smaller from 1 to 10. And 6 is definitely greater than 5. Now here, a chain doesn't have to be straight across. And notice the longest chain here is 7. And I show you either starting from this carbon or this carbon, how to get to 7. And finally, I threw in a real sneaky one. Notice the chain for F. This carbon is bonded to this carbon, to this, and it's bonded to this, number 5, then to 6, 7, 8, 9. And that's the longest chain. There are a couple other chains like 1, 2, 3. Right across would be 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8. Well, of all those, 9 is the greatest. And you need to know the longest chain in order to get the root name of any organic molecule that's acyclic, not in a ring. Now, an important skill you need for organic chemistry, hint, hint, it can be on the test, and that is give the IUPAC name for the following molecules. And the IUPAC name is the official name. Hopefully by now you've all learned the two tables. Let me open them up. And hopefully you've learned this table, which is both of these are available to you for download in the lecture folder of D2L, Desire to Learn. And you should know the alkanes problem set, alkanes names from 1 through 10, and how many carbons there are. And with that, you can draw molecules and you can name molecules. And 1 is methane, 8 is octane, 10 is decane. And you should also know, we'll get to that today, the alkyl groups, 1 carbon, methyl, 2 ethyl. There are 2 different possibilities when you have 3, N carbon of straight, N propyl, 3 carbons, center carbon to ringer chain, isopropyl. For 4 carbons, there are 3, but one of those 3 I've never seen in real use, so I'm not going to teach it to you. But these 2 I have. 4 carbons, the N carbon is N-butyl, and then 3 carbons bond to center carbon, bond to ringer chain, tert-butyl, and starting next week, I'll be lazy organic chemist, and we just call it T-butyl. Tert meaning tertiary 3. So if we look at B, how many carbons are in the longest chain? Well, there's only 1 chain, 6 hexane. Now, on the test, and until we get to fats and oils, that's about week 14, I will not use the paren method, but you can on the test. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's no name. Now, for D and E, they're the same molecule. All I've done is rotated 180 degrees. I just wanted you to see that. And both are longest chain, 4 carbons, butane. And then what's left over is the alkyl group CH3, your old friend, the methyl group. And when you do an alkyl group, you need a number, what carbon it's on. And we use numbering from either end of the chain to give the lowest number to all the alkyl groups. So therefore, this way we start in D from the left, and the methyl group is on 2. In E, we start from the right, the methyl group is on 2. Interesting enough, on a test, if I were to put E, some students would put 3-methyl butane, and I'd mark it wrong, because it is. And let's do G. If you want me to do others, I can. And what's the longest chain? Well, it turns out I made it easy on this, but I might not on the test. It's straight across 9 carbons. That's no name. And then we have this alkyl group and this one. And this is 2 is, oh, it is your old friend, the methyl group. And on 4, 3 carbons, center carbon to the chain, longest chain, that's isopropyl. Now, I hold myself to the IUPAC nomenclature rules for order of alkyl groups. I will not hold you, but on the answer key, I will always put only the correct one. Now here I have 2-methyl 4-isopropyl, no name. You could have also on my test, even though the IUPAC police would come and arrest me if I did it. No, there are no IUPAC police, but if you had put 4-isopropyl 2-methyl, I would mark that correct. Now, you might ask, say, well, how come the isopropyl I isn't before M? If you look at the IUPAC rules, prefixes like iso, N, or tert are not considered for alphabetical priority. isopropyl is a B, which is why it's after M. If I got my alphabet right, I hope I did. Now, for a ring, remember every bend in a line is a carbon, every end in a line, well, I'm not doing that in this class, but every bend, 1, 2, 3, 4, 5, 6, hexane. Then for ring, we use the prefix cyclo. Have everybody's attention. On test number 1, I see people write down for this hexane, and that's wrong because hexane is acyclic, not a ring. Do not forget to put the word prefix cyclo when you're doing a ring. Otherwise, it's wrong. I've seen it too many times, and that's why I started a while ago telling students that's a common mistake on test 1. Make sure you don't do it. Remember, for a ring, you need a prefix cyclo. Now, if we look at I, 6-membered ring, cyclohexane, oh, an isopropyl group. Now, when there's only one substituent on a ring, you do not use a number. When there's only one substituent on a ring, you don't use a number because every carbon, whatever it's on, is carbon 1. Then everybody knows that. And here, oh, cyclopentane ring J. Doesn't that look like the little greenhouses in Monopoly? You people still play Monopoly? Or when you were a kid? All right, now let's look at K. K is a case where I would accept 4 different answers, but I always try to give the correct IUPAC answer. First of all, oh, we have a ring. How many carbons? 1, 2, 3, 4, 5. Cyclopentane. Cyclo, because it's a ring, pentane, 5 carbons. And on there's an ethyl group and a tert-butyl group. Now, the IUPAC rules are the alkyl groups, when there are no other functional groups, which there aren't in this ring, the alkyl group with the highest alphabetical priority, closest to the front, gets the lowest number. And the others, number clockwise or counterclockwise to get the lowest numbers too. Therefore, forget the tert, B is first. So tert-butyl is on carbon 1. And if you go clockwise, the ethyl group is on carbon 2. Now, I'd accept 3 other answers. If you put 2 ethyl, 1 tert-butyl, I'd accept that. If you put 2 tert-butyl, 1 ethyl, I would accept that. If you had 2 ethyl first and 1 tert-butyl, I would accept that. But in reality, this is the correct IUPAC name, but I'm going to give you a special gift on that. All right, there are 2 types of the main nomenclature questions. The first one we just did, give the IUPAC name, and I'll never ask on tests, even though I think it's cool to say IUPAC is the acronym for International Union of Pure Applied Chemistry. That's cool, but I'm a chemist, so I think that. But that means the official name. So give the name. The other type of nomenclature, remember nomenclature is a fancy word for naming, is draw the condensed structures. That means you don't show the bonds between hydrogen and carbon for the following IUPAC names of molecules. Well, first of all, you have to know the table, and butane, 4 carbons. And the other thing you need to know, there's 4 bonds to, oh, it's still broken. 4 bonds to carbon wants to go over there. Oh, now the other one does. 4 bonds to carbon, 4. Yes, 4 bonds to carbon. That's your friend. Any structure you write on a test, do 4 bonds to carbon. Make sure there are. So if you look at butane, first carbon does have 4, second one does, third and fourth, they all have 4 bonds. Now in here, I didn't write the lines between the carbons like I do normally. You can do it either way. Now, if I look at octane, 8 carbons, I did show the lines. Now let's look at F. How do you decode this to know what to draw? You start from the right and move left. Hexane, 6 carbons. Methyl, CH3. Di means 2, tri means 3. And the 2, 3, and I forgot a hyphen between the 3 and the D, bad Dr. White. Anyways, they are on carbons 2 and 3. Now you could have started writing for numbering from the right, going left and put it on this carbons, and either way would be correct. So next, butane cycle. We call this a ring, even though you think it's a square. That's a 4-membered ring. And here again, starting from the right, going left, cyclo or hexane 6, cyclohexane 6-membered ring. And then we have isopropyl, and you can put it on any carbon. Most of you probably put it on the top, right? And all I'm doing is rotating this around. Now, I did make a mistake myself. Even I make mistakes. This should be 1-tert-butyl 2-ethyl. And I wrote it this way. There are many other ways that can write it. Let me show you. And this would be one, another one, which would be perfectly correct, which I think a lot of you might have done one of these too, even though I did a different one. And either of those would be correct. And if you're ever unsure, see me after class and hold it up to your screen, and I'll tell you. All right, and if we look at this 2,3,5 trimethyl octane, start at the right octane, 8 carbons, methyl group CH3. Tri means 3, remember di means 2. And where are those 3 methyl groups? On carbons 2, 3, and 5. I start here 1, that's 2, that's 3, 4, and that's 5, and they're methyl groups. And it's your old friend propane. Any questions so far? Remember, there's no such thing as a dumb question. All right, now another type of question I will ask on test 2, 3, and 4, and the final is give the reaction product or products for the following reaction. And how do you do that? You look at a chemical reaction. Hopefully you've memorized the general chemical reactions we've gone through. In this case, you say, what's CH3, CH2, CH3? It's a hydrocarbon. What's O2? Oxygen. And I don't have it written here, which I normally do, so I better go to here. And this is an alkane. A molecule that's acyclic with only carbon, hydrogens, and carbon-carbon single bond. But it could have also been a cycloalkane, a ring with only carbon, hydrogens, and carbon-carbon single bonds. And the general reaction is an alkane or a cycloalkane plus oxygen. In real life, you need a heat source or spark, gives CO2 plus water. And you should memorize these general reactions because those are your maps to help you go to the right answer on the test. And therefore, alkane, oxygen, I'm going to get CO2 plus water. And if you look at B, It's the same thing in alkanes, oxygen, and this is the beauty of functional group organic chemistry. We get the same products, CO2 and water. If you look at C, the last one in the problem set, I have a ring, cyclohexane, and if we go back with oxygen, cyclohexane is an alkane. And any cycloalkane with oxygen will give me CO2 and water. So the answer here is CO2 and water. And that's how you do it. Any questions on the problem set or anything to do with alkanes? I have a question. Did any of you, since we met last, drive by a gas station and think half the gasoline weight they sell is an alkane? Did you? Did you happen to turn on your stove to cook something and think the gas you're burning, methane, that's an alkane? I hope you do. Or did you happen to look at a candle and see it burning and think half the weight of that candle, it doesn't have to be burning, but it looks nicer when they're lit, is an alkane? Remember, organic chemistry is all around you. I stole that from SpongeBob. And it won't hurt you to think about it when you're not in my class. Trust me, I'm a chemist. Did that work? Organic chemist. How about trust me, I'm a doctor? Did that work? Think about organic chemistry. All right, now something I promised I'd do today, and I'll be cutting out of the video, but I think you'll find it useful right now, and it'll take about 10, 15 minutes at most. I'm going to teach you a method that eliminates test anxiety. Or not alkanes, alkenes. And we were talking about addition reactions. And I talked to you about hydrogenation, where you break the pi bond and each carbon of a double bond you break the pi bond and each carbon of the double bond, remember there's one pi bonds we break, sigma bond, you should know a double bond has one pi bond, one sigma, you don't break, and each carbon of the double bond gets a hydrogen. I also showed you halogenation, and again, double bond. Remember, X is the halogens, fluorine, chlorine, bromine, or iodine. And you don't need a catalyst for this. And each carbon gets a halogen. You break the pi bond. And we did examples of this. Now, this was symmetrical addition. I talked about Markovnikov's rule, which I will never ask on a test. What's Markovnikov's rule? But it's here the confusing way. The better way is the carbon of the double bond with the most hydrogens gets the H from, in this case, HX, and the other carbon gets the X. For this, HX is hydrochloride, hydrobromide, or hydroiodide. HF, hydrofluoric acid. You try and stay as far away as possible. And here, you break the pi bond. One carbon gets H, one carbon gets X, and it follows Markovnikov's rule. The carbon of double bond with the most hydrogens gets the hydrogen and the other carbon gets the halogen. And that's Markovnikov's rule, or as I learned it long ago, the rich get richer and the poor get poorer. And we're talking about hydrogens. And I haven't had a chance to share with you today. So what would be the organic product or products for a following reaction? 3 points each. And don't forget, for those who came in late, I had a special gift for the whole class. You've been so nice to me. Take Monday off. Just tell anybody at ECC, Dr. White said I didn't have to come to any of my classes. You can take the rest of your classes too. Remember, it's Labor Day. And for those who are turning on your webcam, thank you. For those who can't, thank you for coming to my class. And when you're done, give me a thumbs up. All right, I think everybody's done. Remember, when you look at a molecule now, look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen? Oh, look, a double bond. The rest are carbon-carbon single bonds, carbon or hydrogen. So immediately all I see a double bond reacting with, iodine is a halogen, HX. You can write it this way, or you can write it, this way. Both of these are the same thing. Organic chemists write it, and after a break, I'll tell you. Break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule. And if we look at the carbons that double bond, this has 0 hydrogens, and this has 2 hydrogens. Now you have to use your high-level math skills. Which one's the larger number? And hopefully I'll pick 2. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across. I have my 2 methyls. Notice these 2 carbons, I broke the pi bond. The carbon at the end with 2 hydrogens gets the hydrogen, and the other carbon gets the halogen, in this case, iodine. And I know there are 4 bonds to carbon, so I can put in my hydrogens. And that's how you do it. Oh, by the way, this is an ugly looking 2. That's better. And that's how you do it. If I look at the clock, oh no, I went a whole minute off to our break. Let's take a break, come back in 5, come back at 1:56. I'm going to get up and stretch. Time to get going. I also have this whistle I can use too. I found in Zoom to get everybody back, it works good. All right, let's get back to work. And let's do another one of these. Now, I haven't mentioned it, but I better mention it now. Mother Nature, who is the greatest of all organic chemists, and Dr. White love rings. Students hate them. Oh, students don't like rings, but I like them. I love them. And let me do this one, then I'll give you one to do. And the question is, again, give the organic products. I better write it out. And whenever I say give, that means draw. And I put the S here in case there's more than one later in the semester, we will have that case. Well, if I look at this, I say, oh, I know, look for what's different. There's a double bond. I'm reacting with HCl, which is HX. Remember, X equals chlorine, bromine, or iodine. And I break the pi bond. Remember, double bond has one pi bond. You break easily. And a sigma bond, you don't break at all. And one carbon gets H of the double bond, the other gets X, and it follows Markovnikov's rule, which is the carbon double bond with the most hydrogens gets the hydrogen, and the other carbon gets the halogen. I look at the ring, wait a second, I don't see any hydrogens. What do I do? Well, there are 4 bonds to carbon. If we look at the 2 carbons here, we look at the top one, there are 1, 2, 3 lines to it, 3 bonds. How many bonds should there be? 4. 4 minus 3 equals 1. So there's 1 hydrogen there. We just don't show it. We don't know how to write 1 either that well. When I first got this pad to have to teach, the tablet I'm using, I spent about 3 days of Friday, Saturday, and Sunday practicing writing. I'm still always not good. And now if we look at the other carbon right here, it has 1, 2, 3, 4 bonds. Don't forget this bond to the methyl. And 4 minus 4 equals 0. So this has 0 carbon hydrogens. So which number is greater, 1 or 0? Time's up. Hopefully all pick 1. And Markovnikov's rule is the hydrogen goes to the carbon with the most hydrogens of the double bond, and the other carbon gets the halogens. Well, you break the pi bond. Do you break carbon-carbon single bonds? No. So the methyl group, CH3, is still there. This carbon here, we don't show hydrogen, so I'm done. This one will get the halogen, chlorine. Now, you could have also written it this way, and for this class, it doesn't make a difference. And that's how you do it. Now, let's look at the carbon here, which becomes this carbon. Here it had 1 hydrogen. I'm going to make you work today. How many hydrogens on this carbon right here? Well, let's count the bonds. How many bonds or lines? 1, 2. And how many bonds should carbon always have? 4. and 4 minus 2 equals 2. So that means there's 2 hydrogens. And yes, we did add this hydrogen to that carbon. We had 1, and now we have 2. And that's why students don't like rings and Dr. White, Mother Nature do. Well, now I'm going to be a nice guy and let you try it. Oh, did I do that? Ah, hold on. All right. And this is your turn. What would be give the organic product or products for the following 3 points each? Remember, these reactions are the way organic chemists make compounds that we use in our everyday life, or make compounds that are further reacted to use things you use in your everyday life, like medicine, your fabric softener, your other things you use all around your home and your daily life. These are the way we build molecules for those products. All right, anybody need more time? All right, let's take a look. What do we have that's different? Double bond right here. What are we reacting with? HBr, Br is a halogen, HX. For this reaction, X can be chlorine, bromine, or iodine. And just to remind you, every reaction I'll ever do in this class, underneath I'll write the general reaction. However, on a test, some of my very best students, every problem like this, they write the general reaction. Some of my very best students, they never write it, but they do know it. And what happens? You break the pi bond, one carbon gets H, the other gets the halogen, and it follows Markovnikov's rule. And I say his name to honor his great work. Well, what's Markovnikov's rule? The carbon of double bond with the most hydrogens gets the hydrogen. Oh no, there are no hydrogens. Yes, there are. Count bonds. This carbon has 1 hydrogen, 4 bonds to carbon. There are 3 bonds to this carbon right now, 1 hydrogen. This carbon has 1, 2, 3, 4 bonds. 4 minus 4 is 0. Which is the greater number? Hopefully you pick 1. Therefore, the hydrogen will go here, and the other carbon double bond will get the halogen, in this case, bromine. Do we break carbon-carbon single bonds? No. And that was, so I still have my ring and my ethyl group, CH3, CH2. But I will break the pi bond, and I did. And this carbon right here will get the hydrogen, so I don't have to show it. And this carbon will get the bromine. And that's how you do it. Any questions on that? How many would like me to do another one? Okay, I have 1 taker. So guess what? It's Special Request Wednesday. And here's another one. Let me clean up that 3. And I feel better. It's your turn to have some more fun. And don't forget, when you're done, thumbs up time. All right, I think everybody's done. When you look at a molecule, look for what's different. Double bond. The rest is just going to come along for the ride. So all I really see now is a double bond. I'm reacting with HCl, that's HX. X equals chlorine, bromine, or iodine. And in this case is chlorine. Dr. White's like loves chlorine atoms. They've been good to me. I've been good to them. Break the pi bond, one carbon gets H, the other gets the X, and it follows Markovnikov's rule. The carbon with the most hydrogens of the double bond gets the hydrogen, the other carbon of the double bond gets the halogen. Oh no, it's a ring. Now we got to count bonds and calculate it. If we look at this carbon right here, it's got 3 bonds, 4 minus 3 equals 1. So that means it has 1 hydrogen. We look at this carbon, it has 1, 2, 3, 4 bonds to it. 4 minus 4 equals 0, and this has 0. So which has more hydrogens? The one with the number 1 by it. Well, do you break carbon-carbon single bonds? No. So immediately I have a ring, and I have my 2 methyl groups. That was a trick instructors do. I snuck this in, and this comes along for the ride. And here are my 2 carbons. Which carbon gets the hydrogen? This one. And so I'm done. And the other carbon, this one, gets the halogen, chlorine. Now, if you put the methyl group here and the chlorine there, that's fine. Let me redraw it. Either one of those would be correct. All right, any questions? All right, listen carefully. There are more examples like this in the problem set, alkenes and alkynes, and we'll go through that. If you still have problems, please feel free to come to my office hour. I have it tonight from 5 to 6:15 on Zoom, different Zoom lab, and I'll be more than happy to help you. Okay? Let's move on. Now, this was addition of an acid HX to a double bond. It turns out another important reaction is addition of water. I hope you all know water is H2O to an alkene, also known as hydration. And here I have this way, but let me show it a better way. Double bond, H plus, and water, and this is the product you get. Now, let me teach you something. H plus. H plus means acid catalyst. And generally, there are different ones, but for this class, the most common one is sulfuric acid, H2SO4. But other ones I could use, which I won't teach in this class, but I personally have used for this reaction, is toluene sulfonic acid and also methane sulfonic acid. You wouldn't want to use HCl or anything because you'd be doing the previous reaction. Now, let's look at water. Another way to think of water is HOH. And what happens in this reaction, one carbon gets the H from water, the other gets OH. And by the way, OH, which I sometimes will call OH, also is hydroxyl group. I'll never ask on tests what's the hydroxyl group, but I'll use that terminology the rest of the semester as standard organic chemistry. Now, this reaction also follows Markovnikov's rule. And the carbon with the most hydrogens, the double bond, gets the hydrogen, the other carbon gets OH, the hydroxyl group. And similar to what we did before. And you'll learn later on, these new type of molecules are called alcohols, which are very useful in our daily life. So if you have an alkene double bond, you can hydrate it, add acid and water, make an alcohol. Let's look at this. Now we're getting in some really exciting, good stuff. And one thing I should mention down here, if you look right here, I have two reactions, 1 and 2, and they're both the same reaction. I can either write it like 2, like you're familiar with, but organic chemists are lazy. Why do I have to write all those plus signs? And we put reagents above and below the arrow. And I just thought I'd show you that. I'd never asked this on a test, but anyways, let's look at this. What do we have going? Look at a molecule. Look for what's different. Double bond. What am I reacting with? Acid and water. Acid H plus is a catalyst. Water, remember, is HOH. And you break the pi bond, one carbon gets H, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. So do you break carbon-carbon single bonds? No. And therefore, I have my 3 carbons. If I look at my 2 carbons of the double bond, are now these 2 carbons. I broke the pi bond. Remember, there's 1 pi bond you can break, 1 single or sigma bond you don't break. And now I have to look at which carbon of the double bond has the most hydrogens. This has 2, this has 1. Which is the greater number? Hopefully I'll pick 2. Therefore, the hydrogen will go to this carbon, and the hydroxyl group from here will go to the other carbon double bond, and the hydroxyl group counts as 1 bond to carbon, so I know how many hydrogens to put in, because there's, oops, I better put myself on the screen there. There's 4 bonds to carbon. Instant replay. You have a double bond. You're reacting with acid and water. Double bond, acid and water. Remember, water is HOH. You break the pi bond. 1 carbon gets H. The other gets the hydroxyl group OH. And you use Markovnikov's rule. the carbon with the most hydrogens gets the H from water, hydrogen, and the other carbon of the double bond gets the hydroxyl group, and you don't break carbon-carbon single bonds. And here's one for you to have fun with. So do have some fun, please. Give the organic product or products to the following reaction. Well, I see one person's done. And when you're done, give me a thumbs up. If you're not, take your time. I try and give everybody time to finish. And don't forget, if you're having any problems, always feel comfortable to ask questions. Well, I see 2 people done, possibly 3. Anybody need more time? Nope. All right, let's do it. What do we have here that's different? Double bond. Remember, look at a molecule, look for what's not carbon, carbon single bond, what's not carbon or hydrogen atoms, and that's where the fun is. That's where the functional group is. Double bond reacting with acid, that's H1 catalyst or H plus catalyst, and water. And remember, water is HOH. And now you break the pi bond, one carbon gets H, the other gets OH from water, and this follows Markovnikov's rule, and that is the carbon with the most hydrogens gets the hydrogen from water, the other gets the hydroxyl group OH. So now we have to look at our 2 carbons of the double bond. Ooh, this is easy. This one has 1, this one has 0, which is the greater number. Hopefully all pick 1. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. This carbon has a methyl group. Here are my 2 carbons of the double bond. I broke the pi bond. Remember, there's 1 pi bond and 1 sigma bond, single bond. And the carbon with the most hydrogens gets the hydrogen. And you could have written this CH2. And actually, let me write it this way, like, and the other carbon gets the hydroxyl group, OH. And I know there are 4 bonds to carbon, so I can throw in or write in the rest of the hydrogens. Let me do that again. Double bond, reacting acid and water. You break the pi bond, 1 carbon gets H, the other gets OH, because water, think of H-OH, hydroxyl, and it follows Markovnikov's rule. The hydrogen goes to the carbon of the double bond with the most hydrogens. The hydroxyl group OH goes to the other. Therefore, we have 1, 2, 3, 4, 5 across plus the methyl. Here are my 2 carbons of double bond. This carbon has 1 hydrogen, the other is none, 0. And therefore, the hydrogen goes there, hydroxyl goes there, and that's what you get. And let's do another one. Give the organic product or products for the following. Well, I see one person's done. I'll wait for everybody else to be done. Then there was 2. And 3. All right, I think everybody's done. Let's do this. Look at a molecule, look for what's different. Double bond. I'm reacting with acid and water. H plus is acid catalyst. Remember, water is H, OH. So I break the pi bond. 1 carbon gets the H of the double bond. The other gets the hydroxyl group OH. And it follows Markovnikov's rule. Years ago, I used to spend a lot of time wasting your time writing out Markovnikov's name, which I'd invariably get wrong. And I just decided I'll just put M, but I still say his name. So here are my 2 carbons of double bond. This has 2 hydrogens, this has 1, which is the greater number. Time's up. Hopefully I'll pick 2. Do you break carbon-carbon single bonds? No. I have 4 across. Here are my 2 carbons of the double bond. This carbon gets the H because there's 2 hydrogens. The other carbon gets the hydroxyl group. And I put in the hydrogens. Remember, there's always 4 bonds to carbon. Hydroxyl group counts as 1 bond. And that's how you do it. Oh, let's do one more. Let's have really a lot of fun. And there you go. Have some fun. And when you're done, don't forget, give me a thumbs up. If you want, you can use the emoji. I'd like to rename it Symboli because it's really a symbol. I don't know where they got the name emoji. But anyways, I don't think they're going to change it for Dr. White. All right, let's do this. If we look at this reaction, what's different? What's not a carbon-carbon single bond, carbon or hydrogen atoms, double bond. Everything else is going to come along for a ride. Reacting with acid catalyst, that's what H plus is, and water. And remember, water you can think of for this reaction is H and OH. And you break the pi bond, one carbon gets H, the other gets the hydroxyl group OH. And it follows Markovnikov's rule. And if we look at, it's a ring again, Dr. White and Mother Nature love rings, students don't. And here are my two carbons. I have to count bonds to count hydrogens. If I look at this carbon right here, it has 3 bonds to it, 4 minus 3 equals 1, so it has 1 hydrogen. If I look at this carbon right here, it's got 4 lines or bonds to it. 4 minus 4 is 0. So this one has 0. Which is the greater number? Hopefully I'll pick 1. I hope so. Will you break carbon-carbon single bonds? No. So I have my ring. I have my methyl group. The carbon with the most hydrogens, this one gets a hydrogen, but I don't show those on a ring. And the other one gets the hydroxyl group. And you could have also drawn it this way. And that's how you do hydration of a double bond to make, and I'll teach you in a couple chapters, molecules with hydroxyl groups are called alcohols. And that's that. Any questions on this? All right. Well, there's some other reactions we'll learn later on with double bonds, but for now, it's time to go back and talk about triple bonds. Now, a triple bond, remember, 3 lines between 2 carbons. This is a triple bond. Remember, each line is a pair of electrons, and we call that an alkyne, Y-N-E-N-D. Well, the first thing is, how do you name this? Well, the ending Y-N-E is used to designate a triple bond. Forget about diene, I'm not going to teach that. You find the longest chain that contains both carbons, in this case of the triple bond. And you number it just like you did a double bond. So the lead carbon of the triple bond has the lowest number. So let's take a look at how you name. All right. Does everybody see the alkyne, the triple bond on your screen? I think so, because all right, now, question is, give the IUPAC name. And IUPAC means the official name for, and say this one. So what do? We look for what's different. Ooh, a carbon-carbon triple bond. How many carbons in the longest chain with both carbons of the triple bond? I don't know, you better start counting. 1, 2, 3, 4, 5, 6. Now, hopefully by now, you've learned the alkane chart. 6 is hexane. But for a triple bond, ANE ending is dropped and it's changed to YNE. So this would be hexyne. Now, what is the lead carbon closest to the end of the chain of the double bond? And the answer is 2. If we start from the other side, it'd be 1, 2, 3, 4. Which is smaller, 2 or 4? And the answer is 2. So that's 2-hexyne. Let me do one more before I let you loose and have you have some fun. And don't forget the 3 lines mean 3 bonds to carbon. Now let's take a look at this compound. The question is, what's the IUPAC name for this? And find the longest chain. 1, 2, 3, 4, or you can come down here 4. Either one will give the same answer. 4 carbons is butane. However, for a triple bond, ANE ending at the end of butane is dropped and it's replaced with YNE, butyne. And which carbon of the triple bond is closest to the end of the chain? And that's the side numbering that 1. Oh, look, on carbon 3, we have your old friend, the methyl group. And therefore, it's 3-methyl-1-butyne. It would not be 2-methyl-3-butyne because the triple bond carbon gets priority, lowest number. Again, the triple bond carbon in an alkyne gets the lowest number. Now, good news, because of the linear nature of a triple bond, meaning it's straight across, until you get to some monster rings, you're not going to see a triple bond in a ring. In fact, I think, and I've got to really think, I think I saw many decades ago, I saw some paper where some guy was showing off. That's a publication in an organic journal. Oh, look, I made a ring with a triple bond. I think there was 18 or 20 carbons. Why you'd want to do that to this day, I don't know. Maybe someday there might be a use, but in real life, you're not going to see it in a triple bond or ring. So we don't have to do cyclic alkynes, because for all intents purposes in real life, they just aren't there. So it's time for you to have some fun. And what would be the IUPAC name for the following molecule? 3 points each.
Dr. White, I have a quick question.
Go ahead, by all means.
On the previous one we just did, do you have to put the 1 in front of the butane, or can you leave it? I can't remember what we talked about
that's
previously.
A very good question. Okay, and the answer to that is yes, you do. Because if I were to write this, by the way, wrong, so everybody knows, if I see this, well, where the heck is the double bond? Is that carbon start at carbon 1 or carbon 2? I don't know. I have to guess. IUPAC names, you never have to guess, which is why this one is necessary. because without the one, I got a question mark. Where is it? And you'd never, ever have to guess at where a position is of a functional group. So Calvin, excellent question. Thank you. And like I keep on telling you and telling myself, even though I do know it, there's no such thing as dumb question. All questions are good questions. And the most important thing for you and everybody else, you won't make a mistake by forgetting that number. And when you're done, you know the drill by now, hopefully. Give me a thumbs up. If we're in a classroom, I could see when everybody's done, but I also say, when you're done, look up and smile. And people sometimes do and sometimes don't. All right, let's get to work. Let's look at this molecule. What's different? What's that, a carbon-carbon single bond or carbon-hydrogen atom? Triple bond. Alkyne. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6, 7. 7 carbons. Heptane, but triple bond, A and E ending of heptane, drop the A and E and replace it with Y and E. Heptine. Say that 5 times quickly. No, you don't have to. Now, which carbon is the carbon of the triple bond closest to the end of the chain? And there are 2 ways you can number it. If I go from right to left, the lead carbon is 3 of the triple bond. If I go from left to right, the lead carbon is 4. Which is the lowest number? Hopefully I'll pick 3. And that's how you get 3-heptine. Oh, let's do another one. Remember, di is 2, tri is 3. Have fun. That looks better. I got one person done. Yay. There's no race though. Doesn't it feel good you can do organic chemistry? And the last stuff with Markovnikov's rule, you were doing some serious, very serious organic chemistry. And hopefully it wasn't too painful. All right, anybody else need more time? All right, let's do it. Question is, what's the IUPAC name for this molecule? What's different? What's not a carbon-carbon single bond or a carbon-hydrogen atom? It's a triple bond. How many carbons in the longest chain? 1, 2, 3, 4, 5. If I come up here, 5, come up here, 5. They're all 5 carbon. Alkane is pentane. But triple bond, A on the ending of pentane is dropped and replaced with pentine. Now, what's the lead carbon? If I go from this way, it's 2, the other way would be 3, and therefore, what's the lower number? 2. So it's 2-pentine. And then on carbon 4, I have not 1, but 2 methyl groups. How do we show that? Di. Now, similar to Calvin's question earlier, when you have 2 groups, you have to have 2 numbers, even when they're on the same carbon. Because if you don't, I've got to guess where the second one is. And here, this would be 4, 4, dimethyl 2-pentine. Triple bond, Y in the ending. 5 carbons in the longest chain, pentane becomes pentine. Lead carbon, 2 of the triple bond to the end of the chain. And then on carbon 4, 2 methyl groups, 4, 4 dimethyl. And that's how you do it. Any questions on this? Don't forget, time for commercial from Dr. White. Tonight, I have my office hour from 5 to 6:15 on Zoom, so you don't even have to drive to ECC to meet with me. If you have problems, stop by, I can help. Also, if that's not a convenient time for you, email me and let's see if I might be able to set up other office hour times that might work for you. And with that, it's time to take a 5-minute break. Come back at 2:50, 5 minutes from now, and we'll continue. Remember, I'm trying to make up lost time for Monday. Oops. Time to get going. All right, we're talking about nomenclature, naming of organic compounds, the alkynes triple bond. There are two types of nomenclature skills you should have, meaning two types of questions I can ask on a test. Number one is, here's the product, here's the compound, give the IUPAC name. The other is, here's the name, draw the compound. And let's take a look at one. And let's take a look at 3-octane. How do you know what to draw? Well, you start from the right and move left. Y-N-E ending, triple bond. And if that were A-N-E, octane, that's 8 carbons. Now you can start numbering from either side. Most of you will do this. So at carbon 3, I have my triple bond, and now I know there's 4 bonds to carbon. And I know how many hydrogens to put in. And remember, now it's your solemn responsibility as a student in my class to let me know if I ever make a mistake on drawing the number of hydrogens in. Oh, I just got burped on. Hold on one second. Yep. All right, sorry about that. I don't know why every once in a while it hangs up on me, but it does. All right, let's talk about draw the following molecule. Let's do another one. Hold on one second. And let me do this one, then I'll let you try one, because it's only fair to let you have some fun. And the question is, draw the structure for 4-tert butyl 2-octane. How do you do that? You start from the right and move left. Y on the ending, triple bond. If that were A and E, it would be octane, 8 carbons. Oh, I just did 8, but I'll do another. I guess I got 8 on the mind, on my brain. Now, where's the triple bond between carbon 2 and 3? And if we call this 1, 2, 3, 4, 5, 6, 7. Ooh, I didn't do it right. 5, 6, 7, 8. I'll get it right eventually. Now, we have let me get this out of the way. We have a tert butyl group on carbon 4, which is this. And now I'll draw in the hydrogens. Remember, there's 4 bonds to carbon. And I'm done, which means it's your turn to have some fun. But first, I'll give you time to check. All right, everybody done so I can move forward? If not, say stop. All right, I'll leave that up. Let's have you try one. And why don't you draw the structure for 3-decene? All right, I think everybody's done. Let's do this. How do we do this? You start from the right and move left. Y on the ending tells me triple bond. And if we're A on the ending, it would be decane. Decane is 10 carbons, so I better get to work. And now I have 10 carbons. Where does the triple bond start? Carbon 3. Show that by 3 lines. And now there are 4 bonds. Yes, 4 bonds to carbon. So I know how many hydrogens. And that's how you do it. And I have 3, 6, 9, 10. I got it right. Yay. Oh, let's do one more. and that would be 3-methyl 1-pentyne. Someone have a question?
Hey, got out at 3.
What? Excuse me, Megan, could you repeat it again?
Oh, I didn't know I was unmuted.
All right, are you on track now? Give me a
Yes.
thumbs up. Okay. And all questions are, originally I had them structure a number there that wouldn't work. And that's part of the problem with doing examples on the fly. Like I don't have a list, see, no list of what examples. I just do it on the fly. All right, everybody ready? Get set. I'm gonna go. All right, how do you name this? Or how do you know what to draw the structure from the name? You start from the right, move left. Y-N-E ending, triple bond. That were ANE pentane, 5 carbons. Where's the double bond start? Carbon 1. I'll do it this way. You could have also done on the other side here, but most of you won't. And then on carbon 3, oh, it's your old friend, the methyl group. 1, 2, 3. Now you could put the hydrogen there, or you could put on this end the hydrogen there. And that's how you do nomenclature of triple bonds. Any questions? Again, Y-N-E ending triple bond, or A-N-E pentane, 5 carbons, 1, 2, 3, 4, 5. The double triple bond starts at carbon 1. And then on carbon 3, it's your old friend, the methyl group. And good news, there's no triple bond in a ring that I've ever encountered. All right, now let's go through this again. Alkynes are acyclic unsaturated hydrocarbons with 1 or more triple bond. And here, the triple bond is linear. That means the bond angle is 180. I'll never ask that in test, but let's talk about they undergo the same reactions as alkenes, except you have not 1, but 2 pi bonds. A triple bond now has, and this you should know, 2 pi bonds and 1 sigma bond. Pi bonds, I can break like that. Sigma bond, no, no, no. And I've already gone through this. Oh, one thing, since the triple bond is linear, straight line, you can never have cis-trans isomerism, cis-trans structures like you can have in a double bond. But the key thing here is we've done the nomenclature. Remember, a triple bond has 2 pi bonds, 1 sigma bond. Now, let's look at the first reaction, and I'll rewrite it. Remember, R is anything with carbon and hydrogen, but I'll even more easier way is hydrogenation of a triple bond. Can everybody read handwriting? Hold on one sec. Nope, it's not. the President of the United States or the Prime Minister of England. So I'm not going to answer it. Hold on, one more ring. My answer machine will pick it up. Oh, they gave up early. Now, if you take a triple bond, remember this is 2 pi bonds and 1 sigma bond. And what we do when we react with hydrogen is, since each pi bond you get a hydrogen on a carbon, 2 pi bonds, you'll get 2 hydrogens on a carbon. Now, something new to teach you. Everybody see bracket, excess bracket next to the H2? Well, organic chemists are lazy. And instead of having to balance this equation, because you're using 2 molecules or 2 moles of hydrogen, remember moles, chemist counting unit, organic chemists are lazy. And bracket, excess, close bracket means excess. And that means when you see it, I have all the hydrogen in the world that can react with anything hydrogen can react with. And in this case, the 2 pi bonds. And that's hydrogenation of a triple bond. And I'll do this one, 3 points each, give the organic product or products are the following. And by the way, for those of you who have visitors with you, say hello from Dr. White. And what do we see that's different? Triple bond. What are we reacting with? Excess hydrogen, which means excess in brackets, means I have all the hydrogen in the world that hydrogen can react with, pi bonds. I have a catalyst. In this case, the catalyst can be nickel, platinum, or palladium. And remember, this has 2 pi bonds, 1 sigma. And I break the 2 pi bonds. Each time I break a pi bond, each carbon of the triple bond gets a hydrogen. 2 pi bonds, 2 hydrogens each. And do you break carbon-carbon single bonds? No. But I broke the 2 pi bonds, and these 2 carbons each get 2 hydrogens. And that's how you do it. Oh, I did it on the, I didn't go to my whiteboard. I should go to my whiteboard now. Hold on. And here's one for you to have fun with. Give the product or products for the following. Don't forget, you're learning these reactions which allow organic chemists and also Mother Nature to make things or to react things to break them down. Later on, we'll learn how Mother Nature uses some of the reactions. I'm going to teach you how to break down your food in your stomach. That'll get exciting. All right, I think everybody's done. Let's take a look at this. What's different? What's not a carbon-carbon single bond or carbon-hydrogen atom? By the way, in a couple weeks, we may have nightmares hearing me say that. I hope not. And we have a triple bond. The rest is just going to come along for the ride. I'm reacting with hydrogen, but excess hydrogen, which means I have all the hydrogen in the world that can react, anything that can react with hydrogen. And I have a catalyst. Remember, catalyst can be nickel, platinum, in this case it is, or palladium. And that just makes the reaction go quicker. You break the 2 pi bonds. The sigma bond you don't. And each carbon of the triple bond gets not 1, but 2 hydrogens because they're 2 pi bonds. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across plus a methyl. 1, 2, 3, 4, 5 across plus the, whoops. Let's get our alignment better. Plus the methyl. Here are my 2 carbons of the triple bond. And notice I broke the 2 pi bonds. And each one gets 2 hydrogens. And now I can put in the rest of the hydrogens because I know there's 4, yes, 4 bonds to carbon. And that's how you do hydrogenation of a triple bond. Remember, the excess in a bracket means all the hydrogen in the world that can react with anything hydrogen can react with. And remember, if you ever have any questions, say, stop, Dr. White, I have a question. Or any other way you want to get my attention. All right, let's move on. Now, next reaction I want to talk about is halogenation. And just like in a double bond, when you react the triple bond, which has 2 pi bonds, not 1, and because we need more than 1 molar molecule, I'm going to be a lazy organic chemist and use the concept bracket, excess bracket, tells me I have all the halogen in the world that will react. Anything will halogen will react with. Remember, X in this case is fluorine, chlorine, bromine, or iodine. And I break the 2 pi bonds. And for each pi bond, each carbon of the triple bond gets a halogen. 2 pi bonds, each carbon gets 2 halogens. And that's how that works. Let's try that again. I almost drew a structure with 5 bonds to it. No way. Ain't gonna ever happen. That's good English. And let's look at the following reaction. And the question is, give, which I really mean draw, if we look at this, look at the molecule, what's different? What's not a carbon-carbon single bond or carbon-hydrogen atom? Oh, a triple bond. Bromine, Br2 gas, is halogen gas, and we have excess. Remember, X for this reaction is fluorine, chlorine, bromine, or iodine. And I break the 2 pi bonds, but not the sigma bond, single bond. And each carbon of the triple bond gets not 1, but 2 halogens. And so therefore, do I break carbon-carbon single bonds? No. I have 1, 2, 3, 4 across. So I'll have 4 across. I'll still have my methyl group here. Here are my 2 carbons of the triple bond. By the way, on a test, you don't have to put dots in there. I'm just, in a classroom, I'd be pointing to this. But if I go like this, you know what I'm pointing at? No. So that's why I came up with the dot. I broke the 2 pi bonds, and each carbon gets 2 halogens, in this case, bromine. And each bromine counts as a bond. And there you go. Well, I better let you have some fun too, so I will. And there you go. What would be the organic product or products for the following reaction? 3 points each. And when you're done, don't forget to do the signal for Dr. White. All right, I see a lot of thumbs there. Hopefully you're not hitchhiking. Oh, is that awful joke? All right, let's do this. Look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen atom should get your attention. Triple bond. We're reacting with excess iodine. Iodine is a halogen. Remember, X can be fluorine, chlorine, bromine, or iodine. And each carbon of the triple bond gets not 1, but 2 halogens, because the triple bond is 2 pi bonds and 1 sigma bond. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 carbons. I better end up with 5 carbons. Here are my 2 carbons of the triple bond. I break the 2 pi bonds. Here are those carbons. Each one, as you can see, gets not 1, but 2 halogens. In this case, it's iodine. And there you go. That's how you do it. Any questions? All right, there are 2 more things I want to cover, which I don't have. Maybe I'll just get the one today and we'll finish next Wednesday. Remember, since all of you are so nice to me, you can take Monday off. Even if you have classes and other teachers, you can tell them, Dr. White said you could take it off. It's Labor Day. And before I forget, I hope you all have a very healthy and happy holiday weekend, Labor Day weekend. All right, let's look at something important. Most of the time in this class, I will make your life easier. Don't tell anybody I'm being nice, ruin my image around here, but I only have one functional group in a molecule. What happens when you have more than one functional group? When it comes to double bond, if a double bond and another double bond is separated by one or more carbons, like this molecule, if they weren't, that's called conjugated, which I'm not teaching in this class because that opens up a whole lot of other things. Each one of these react like it's alone. And notice this molecule has two double bonds. Now, what if we do the following? React that molecule with chlorine, not just chlorine, but excess chlorine. Now, what functional groups, what's different? We have a double bond here. We have another double bond that's away from this by one or more carbons, so each one reacts independently. And you learned if you have a halogen, gas, fluorine, chlorine, bromine, or iodine, each one reacts like it was alone. And therefore, oh, I have two double bonds, so I need more chlorine, but I'm lazy. So I'm just going to use excess. That means I have all the chlorine in the world that will react anything that chlorine will react with. In this case, double bonds. You break carbon, single bonds. No. So I have 5 bonds, 5 carbons, and each pi bond I broke. This one, each one gets a chlorine. And on this side, each one gets a chlorine. And I know there's 4 bonds to carbon, and that's how you do it. And any of the reactions I showed you with double or triple bonds, you can do this with by having them in more than one molecule. Your turn. And when you're done, you know what to do. I see one person's finished, but there's no erase. I give everybody time. I see one more. Thank you for letting me know. And it looks like everybody's done. So if I look at this molecule, I say, oh, a double bond. No, two double bonds, but they're separated by more than one or more carbons, so they react independently. And a double bond reacting with iodine, which is a halogen, which could be fluorine, chlorine, bromine, or iodine. You break the pi bond, each carbon gets a halogen. But since we have two double bonds, I'll put in excess, which means I have all the iodine gas in the world, I2, to react with anything that can react with, which is double bonds. Do you break carbon-carbon single bonds? No. So I have 2, 4, 6. I still have 2, 4, 6. This carbon here, those two are this. I broke the pi bond, each one gets an iodine. And then over on this side, I have these two carbons, broke the pi bond, each one gets an iodine. And I know there's 4 bonds to carbon, and I can put in the remaining hydrogens. And that's how you do it. Oh, let's do one more. These are fun. And why don't you try this one? Let's see if you do this. I'm going to help you out. And here's a little help from Dr. White. On test, I won't, but here I will. And I just remembered, I forgot, who was it who reminded me that I made a mistake in the assignment area and you couldn't upload the signature sheet? I've since corrected that, like I promised I'd do on Monday. So don't forget, upload your signature sheet to the assignment area of Blackboard, please. Oh, I see a couple, one thumb up. Oh, I'm seeing more. All right, it looks like everybody's done. We look at this molecule right here. What's different? Ooh, a double bond. No, 2 double bonds. Remember, when you look for what's different, you're looking for what's not a carbon-carbon single bond, carbon or hydrogen. Well, I have a double bond. They're separated, 2 of them, so each one acts independently, like if we're alone. I have HCl, which is HX. Remember, for this reaction, X can be chlorine, bromine, or iodine. In this case, it is chlorine. And you break the pi bond. One carbon gets H, the other gets X, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogen gets the hydrogen, the other carbon gets the halogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5 across. If I look at these two carbons, I broke the pi bond. This has 2 hydrogens, this has 1. Which is the greater number? Hopefully you pick 2. So the hydrogen goes here and the halogen goes here. Now, if I look at this side, this has 2, this has 1, which is the greater number 2. So the hydrogen goes to that carbon right here, and the halogen goes here. And I know there are 4 bonds to carbon. Oops, that should be a 2. Now it is. And I'm done. And that's something I wanted you to understand. Organic chemistry, even though you have these basic reactions, it can get very complex and also very exciting. Now, I've cheated on you, not really. If we had been face to face today, I would only have gotten 2 50-minute, then we'd have to go to the lab. Since we're not actually doing a safety lab today, I cheated and got more time. So guess what? I'm going to let you out early. Remember, Monday is Labor Day. Have a great holiday weekend. I won't have my office hours unless somebody really needs it. Email me. I'll see if I can show up. Right now, because of the pandemic, don't forget to wear your mask. One of the faculty members made this for me. Isn't that cool? It's a chemistry mask. I don't know if it's safe to wear this to the supermarket. They may call the police. Uh-oh, someone dangerous, but seriously, wear your mask. And I hope all of you have been vaccinated. I have a long time ago. I don't know if I mentioned it. Throughout my life, certain vaccinations and shots don't do well with me. When I got a tetanus shot one time, it paralyzed my whole arm for 2 days. When I got the Pfizer, both shots, no problems. I was so grateful. I had a little soreness in my arm, but next morning it was gone. And they warn you about that. So get vaccinated if you're not. Wear your mask, stay safe. If you have questions, always feel free to ask me, and I'll see you. Guess what? You get a whole couple of days off away from Dr. White, and I'll see you next Wednesday. With that, gang gesund. Goodbye.